Welcome to David Alexander Maths Tuition. This is chapter 12J on sketching gradient functions. So when you've got the equation of a graph, it's quite easy to sketch the gradient function because all we need to do is, well, first of all we need to remember that the gradient function is the derivative of the original equation. So if the f of x is 2x squared plus 5x take away 12, then our derivative, our f dash x or our dy by dx, is 4x plus 5. So I know the equation is 4x plus 5, so I can simply draw that graph. So we know it's cutting through the the y-axis at 0, 5, and it's got a gradient of 4, so quite steep. So it would look something like that. So when we've got the equation of the gradient function, doing the sketch, not really that big a deal. A function has equation 3x cubed plus 2x squared plus 5x plus 7. So the gradient function, this is all the questions asking, what is the gradient function? I guess it's just understanding that the gradient function is the derivative of the original equation. So that is going to be 9x squared plus 4x plus 5. I suppose if we were asked to sketch this, we know it's a quadratic. So first of all, we know it's a U-shaped graph. We know it's got the y-intercept of 0, 5. We could try to factorise and solve it to get x-intercepts, or we could use the quadratic formula solver. In fact, I've just put this through my quadratic equation solver, and it has imaginary solutions. So therefore, it doesn't cut through the x-axis. So what that means is the gradient is always positive because the function is above the x-axis. And I suppose we could work out the turning point by completing the square. And by doing that, we could, I suppose, do a sketch of the gradient function had we been asked to do so. Okay, so a function's got equation, so this is a quartic. So again, the gradient function is going to be the derivative of that. So that's just 20x cubed plus 6x plus 2. So this is going to be very difficult to sketch, but you know, we've not been asked to do a sketch here. Just work out the gradient function. So remember, the gradient function is the derivative of the function, the original function. Okay, so here we've got a quadratic, and we've been asked to draw a sketch of the f dash of x. Okay, so what we need to remember first of all is that a quadratic will always differentiate to a linear equation. So for example, 3x squared plus 6x plus 7, that will go to 6x plus 6, which we know is a straight line, y-intercept of 6, also a gradient of 6. So a quadratic always differentiates to a linear graph. So this is going to be a straight line. So let's consider the turning point here. Now the turning point has got a gradient of 0. So therefore, at this point here, the gradient function will be giving us a 0. So that is going to be our x-intercept, which will be in line with the turning point. Now, the thing is, we don't actually know the equation of this line. I mean, I could maybe make a guess that if it's going through at +2 and -3. Well, we can investigate that in a moment. So let's just say x plus 2, x minus 3. I'll expand that one and see what happens in a moment. Okay, now, at this point here, the gradient is 0. So that is why this point here is a point on the line that is the gradient function. Now, to the left of this line, we can see the gradient is negative. And to the right of the line, the gradient is positive. It's only at this point here, it's 0. So therefore, it's going to be a straight line going through this point here. So it might look something like that. So that would be a rough sketch if there were no numbers, and it's unlikely that you would need to do a sketch where the axes were labelled with numbers. Let's just expand the brackets though, because maybe we can actually work out what the equation of the line should be and whether or not my y-intercept is vaguely okay. I suspect probably not. So it's x squared plus 2x minus 3x minus 6. So x squared plus x take away 6. So if I differentiate this, it's 2x plus 1. So the equation of the line I should have drawn is 2x plus 1. Okay, so it should have cut through there. So it was maybe not quite as steep as it should have been, and the y-intercept was a little bit off, but you know, it wasn't shocking. The most important thing was I got my x-intercept in the right place. So remember, the turning point of the quadratic will correspond to the x-intercept of the straight line. That might take a while to digest. I remember finding this quite tricky when I first got going in maths, but after a while it did sink in. But it's always handy to remember a couple of facts. A quadratic will always differentiate to a straight line. A cubic will always differentiate to a quadratic. A quartic will always differentiate to a cubic. So if you had to sketch the derivative or the gradient function of a quartic, expect to draw a cubic curve. I doubt you'd be asked to do that because that is a little bit on the hard side, but you might be asked to do a sketch where you're differentiating a quadratic, so you'd end up drawing a straight line perhaps. Okay, draw a sketch of f-x. Okay, so again what we've got here is a cubic. Let's just ignore the numbers. So we know that at this point here the gradient is 0. At this point here the gradient is also 0, so I'm just going to assume that that is the origin there. It may not be. Now we need to remember that a cubic graph, so let's say 3x cubed plus 6x squared plus 5x plus 7, will always differentiate to a quadratic, so that would be 9x squared plus 12x plus 5. So we know that this is going to differentiate to a quadratic, and these are the intercepts. So to the left of this point here we can see that the gradient is positive because it's going up, so therefore to get a positive gradient we need to be getting a positive y value, so therefore the graph will be coming down like so. From this point here where the gradient is 0, the gradient then becomes negative, so we are now going to continue to draw. This needs to go underneath the axis and then come back up again through the origin, because this corresponds to the turning point. This turning point means that the gradient is 0, that's why we're getting 0. So it will turn around like so, and then after the turning point the gradient becomes positive. So again, because the line goes up, so again my curve will continue to be above the x-axis, and as we can see that's generating a nice, well, it's not that nice is it, but it's generating a quadratic curve. So can be a bit confusing as I said, but just remember that a cubic, that will always differentiate to a quadratic. So if you're sketching the gradient function of a cubic, you should be drawing a quadratic curve. But the key thing to do is to start off by putting in the turning points. The turning points of the cubic correspond with the x-intercepts of the quadratic curve. Draw a sketch of the gradient function of this curve. So this curve is a quartic. So remember, a quartic will always differentiate to a cubic, so expect to be doing a cubic graph. So the turning points are here. So remember, the turning points means that the gradient function will be 0. So I'll put that there at the origin, and I don't know, it's hard to say exactly where that is, and here. So the cubic is going to cut through these points here. So to the left of this turning point the gradient is negative. It's very negative, and then it's slowing down, it's getting less negative, less negative, less negative until it's 0. So therefore it's getting less negative and less negative and less negative until it's 0. It will look like that. Then it becomes positive, a tiny bit positive, then more and more positive, more and more positive, then less positive. It's slowing down and then 0. So between here and 0 it will go up and then come back down again. And similarly at this point here the quartic curve is not very negative, but then it gets more and more negative, gets very negative, and then it slows down, becomes less negative until it turns around. So as it's getting more and more negative, then it's getting less negative, and then it hits the turning point where the gradient is 0, and then it becomes positive again, a little bit positive and getting more and more positive, so, and then it's just shooting up in this direction. So there we go. So again, the key thing is understanding that a quartic will differentiate to a cubic. The turning points of the quartic correspond to the x-intercepts of the cubic, and then just draw your cubic graph, make sure you go through those x-intercepts. Okay, so how do we draw the gradient function of this one here? So this is a reciprocal. So if I look at to the left of the asymptote, it's always a negative gradient. It's the line or the curve is going down, down, down. So, but let's think how negative it is. It's not that negative here. It's getting a little bit more negative, and now it's getting very, very negative. So if it starts off negative, so we need to be underneath the x-axis. So if it starts off negative and it gets more and more negative, then it's going to look like that. And then of course, as we're going down here, it's going to be like really, really negative. It's in fact so negative it's practically vertical. Now, so that is the sketch of the gradient function of the left-hand side. Now let's consider the right-hand side. Again, it's going down constantly, so it's always negative. So therefore, we are going to have to plot our gradient function beneath the x-axis. It starts off really, really negative. It's getting less negative, less negative, and hardly negative at all here as it's approaching the asymptote. When it, at this point here, it's practically horizontal, so it's almost no gradient at all. It's almost zero. So it's going to go from very negative to not very negative at all. So very negative, and then not very negative at all, and almost, at this point where it's almost horizontal, it will have no gradient, but it will never be completely horizontal, which is why it will never get to a gradient of 0. So it will look like this. Now, if we just think about what does this look like? Well, this is a reciprocal. So it could be a 1 over x. It doesn't look like it's 1 over x, but if it was 1 over x, the gradient function would be pretty similar. So that is x to the negative 1. So if the f of x is x to the minus 1, then f dash x is minus 1 x to the negative 2. In other words, minus 1 over x squared. So we just need to remember that this is 1 over x. This is 1 over x squared, and minus 1 over x squared is a reflection of this in the x-axis, so it would look like so, and that does tally with the sketch that I've drawn. Draw a sketch of the gradient function of this one. So here we can see that the line is continuously going down. There's no turning point, so there's no point where it's going to cut through the x-axis. So here it's not very negative, and over here it is extremely negative. I'll just put very negative. Okay, so if it's not very negative here, it's still negative though, so and then it's getting more and more and more negative, then so at this point here it's now getting I suppose very negative, so our sketch will look a little bit like that. So at this point here, not very negative. At this point here, it's, well, quite negative. At this point here, it's getting even more negative. So we don't need to worry about any values as such, just showing that it's always negative, but just increasing in negativity. Okay, so for this question, we're just sketching the graph of the f of x. We know it's got an x-intercept of -1 and +3, except at +3, because this is a squared root. It's not going to cut through the x-axis there. It's just going to touch it and move away. Okay, so it's cutting through at -1 and 1, 2, 3. So 3 minus 1, and as it's a cubic, it's going to come up and then go down, but it's going to turn around at this point here before taking off. Okay, so sketch the graph of f dash x. Easier if I do it on top of this. So here is a turning point where the gradient is 0. Here is a turning point where the gradient is 0. We know that a cubic, or hopefully we know that a cubic differentiates to a quadratic. So I'm just drawing a quadratic cutting through these points here like so. And again, it makes sense because here the gradient is positive until we get to the turning point. The line of the gradient function is positive at this point here. After the turning point, until the next turning point, it's constantly going down, so it's a negative gradient. That's why this bit is beneath the line. And then after the turning point, hard to see which one's which. Oh yeah, this is the function here. We have a positive gradient, which is why the gradient function is now back above the x-axis again. Okay, so show that dy by dx is this stuff here. So what I'm going to do is expand those brackets. So x minus 3 squared is x squared minus 6x plus 9. And now I just need to multiply that by x plus 1, which will give me x cubed minus 6x squared plus 9x plus another x squared minus 6x plus 9. So just cleaning that up a bit, that's going to be x cubed minus 6 plus 9, minus 6 plus 1 minus 5x squared plus 3x plus 9. If I differentiate that, that will be 3x squared. So dy by dx is minus 10x plus 3. Okay, is that the same as this? I could factorise that, but why not just expand this, as that is easier. So that's going to be 3x squared minus x minus 9x, so minus 10x plus 3. Perfect. Okay, so that is the same as what I've just got to. So use the derivative to determine the exact coordinates of the points where the gradient function cuts the x and y axes. Okay, so this is the gradient function, 3x squared minus 10x plus 3. So if I factorise it, I get 3x minus 1x minus 3. So therefore the x-intercepts will be plus 3. And we can see that it's at plus 3 there, because that was the original, that's the coordinate of the turning point. And here, from the 3x minus 1, is positive 1/3. So this is 1/3 here. And the y-intercept will be, is plus 3. So this point here is 0, 3. There we go. So they are the exact coordinates where the gradient function cuts both axes. Actually, we should probably write